Hi, this is our final lecture on hypothesis testing. Actually, there are a lot of hypothesis testing problems that we have not discussed, but in our short course it is impossible to cover all these topics. So I want to give you the most practically important, the most important for applied mathematics, for applied statistics, hypothesis testing problems. And so our final topic on hypothesis testing is hypothesis on independence. So as you remember, we have already discussed different types of dependence between random variables, between some features that we can measure. So we know that there is a functional dependence, causal dependence, and statistical dependence. And what we are dealing with here in mathematical statistics is statistical dependence. And so today we will discuss how we can answer the question, are two variables independent or not? And how to measure how strong the dependence is, if there is a kind of a dependence between them, a kind of a statistical dependence. But before discussing this, we should understand that variables that we are interested in, so variables of our interest, can be either numerical or ordinal or nominal. So there are three scales of measurement. So the numerical scale, the numerical variable, is such a variable that can be measured in numbers. So that like height, weight, salary, number of some objects of some items, and so on. So for example, salary of a random person, or height of a random person, or number of chairs in a random classroom of this building, something like this. So these are numerical variables. Then there are also ordinal variables. Ordinal variables are such that they cannot be measured in numbers, but we can compare. So we can compare two objects with respect to this variable. For example, school grades. So in Russia, they usually we usually use numbers for school grades, like 2, 3, 4, 5, but these are fictional numbers. Actually, 5 is for excellent, 4 is for good, and so on. So in English-speaking world, they often prefer letters for school grades, like A, B, C, D, and so on. And so we can say that A is better than B, but we cannot express this with a number. So this is an ordinal scale. Or military rank. We can say that colonel, for example, has a higher rank than a lieutenant or than a captain. So, but this also cannot be expressed with a number. So we can just compare whose military rank is higher, of this person or of this person. So, and the third type of variables are nominal variables. So if a variable is nominal, we cannot even compare two objects with respect to this variable. We can only name the value. Like color, we can say that this, for example, this car is white, and this car is black, and this car is yellow, and so on. And we cannot say that color of this car is greater or higher than color of this car. Or gender, we can say that this person is male and this person is female, and so we cannot compare this. We cannot say that gender of this person is greater than the gender of this one. So when we are interested in statistical independence of two variables, methods we usually use depend on what type of variables we deal with. So is this variable a numerical one or pair of variables? Are they numerical or ordinal or nominal? And what you should also know, you should know that it is possible to switch from the numerical scale to the ordinal one and from the numerical and ordinal scales to the nominal one. So for example, if you say that you have, let's say, 100 people and you know their heights in centimeters, so this is a numerical variable, height of a person, you can say, let's rank these people, rank from 1 to 100, so number 1 is the shortest and number 100 is the tallest of them, and so that is how you can switch from the numerical scale to the ordinal scale. After ranking, this variable can be interpreted as an ordinal one. Or you can divide range of possible heights into several intervals, into several categories. Like, for example, you can say that there are 3 types of people: short people, normal people, and tall people, for example. And you can say if somebody's height is lower than 160 centimeters, this person is short, and if it is from 160 to 180, it is medium, and if someone is taller than 180 centimeters, this person is tall one. So, and that is how you can switch from the numerical scale to the nominal one. So you can say that now, let's assume that a person's height can be either short or medium or tall. So 3 values. So that is how you can change a scale if you need this for some purpose. And it is impossible to switch from nominal scale to the ordinal scale or to the numerical one, and from ordinal to the numerical. So I just showed how this switch can be done with arrows. So let's now discuss our independence problems, and let's start with the nominal scale. So we are interested in independence of 2 nominal variables. Different terminology is used here. Sometimes they say that we are interested in whether the 2 variables are independent or not. Sometimes they say that we are interested in whether there is an association between these 2 variables or not. So independence is synonym for no association. Dependence is a synonymic term for presence of an association. So and sometimes the test we will discuss now is called no association test. So what are our observations if we are interested in 2 nominal variables? So let's say that we have 2 nominal variables, a and b, and a has k possible values and b has m possible values, namely a1, a2, ak, and b1, b2, and so on, bm. So, for example, a is gender, and a1 is male, a2 is female, and b is, let's say, hair color, and b1 is blonde, b2 is red, b3 is like brunette, and so on. So, and we have observations. For example, we have 100 people examined, and for each person we know the gender and we know the hair color. And so we know how many, for example, blonde males and how many blonde females and how many red-headed males and how many red-headed females and so on there were in our observations, in our sample. And these numbers that you can see in this table show us number of observations such that so Nij number that you can see in the ith, jth cell of this table, nij, is a number of observations such that A is equal to AI and B is equal to BJ. For example, if A1 is female and B1 is blonde, then N11 is number of blonde women in our sample, in our random sample. Numbers in the last column and the last row of this table are called marginal totals. So these N1 dot is sum of numbers of the that are in the first row. N2 dot is sum for the second row, and so on. So if A1 is female, then N1 dot is total number of females in our sample. If A2 is male, then N dot 2 is total number of males. Then N dot 1, N dot 2, N dot 3, and so on are sums for the respective columns. So N dot 1, if B1 is blonde, then N dot 1 is number of blonde people of both genders in our sample, and so on. So, and N without indexes is the sample size, total number of observations. So a table of this kind is called a contingency table. So if you have observations on two nominal variables, this is the standard way to present results of your observations in the form of a contingency table. So, okay, these are observations. What we can do then? Then, as we are interested in dependence or independence of our variables, let me remind you the definition of independence. So the definition that we use for random events, two random events, A and B, are called independent if probability that they will happen together in the same experiment is equal to product of their probabilities. So they are independent if probability of A intersection B is equal to P of A times P of B. So that is how we can mathematically define what are independent nominal variables. So if for all i's and j's, P of AI intersection Bj is equal to P of AI times P of Bj, for all possible pairs of I and j, if this is true, then we say that nominal variables A and B are independent. So if there is at least one pair ij such that this inequality is false, this equality is false, so then we say that variables A and B are not independent. So, and these are a pair of hypotheses we are testing here, we are going to test. So we say that the null hypothesis is hypothesis on independence of A and B. So we can say that the null hypothesis is that variables A and B are independent, or we can say that is the same, that the null hypothesis is that there is no association between A and B. And the alternative hypothesis is that they are not independent, or that there is an association between A and B. Okay, so this is our pair of hypotheses. How we are going to test these hypotheses. You see here that hypothesis is formulated as a hypothesis on some probabilities. So we are interested in whether some probabilities are equal to products of some other probabilities and so on. And all these probabilities are unknown. So what we are usually doing when we are interested in some probabilities and these probabilities are unknown, we are trying to estimate. We are estimating these probabilities. And the best way to estimate an unknown probability, as you know, is a sample proportion. So that is what we do here. We are using sample proportions to estimate unknown probabilities that we can see in our hypothesis. So Pij is probability of AI intersection Bj, can be estimated as Nij divided by N. So N is total number of trials, sample size, and Nij is number of observations such that A is equal to AI and B is equal to Bj. So this is the natural way to estimate the probability in the left part of our equality that we see here in the null hypothesis. Then two other probabilities can be estimated in a similar way. So Pi dot is probability of AI, and it can be estimated as Ni dot divided by N, and P dot j can be estimated in a similar way as N dot j divided by N. So these Pij hat, Pi dot hat, and P dot j hat are sample proportions that are estimators of our three probabilities we are interested in. So then the test statistic is based on these estimators. So as you can see in the first formula, so in the numerator you see difference between Nij divided by N, so the first sample proportion, and the product of the two others. So you subtract estimators of Pi dot and P dot j from the estimator, so product of these two estimators from an estimator of Pij. And so if the null hypothesis is true, if this equality is true for the probabilities, then it is almost true for sample proportions. So if Pij is equal to Pi dot times P dot j, then Pij hat is almost equal to Pi dot hat times P dot j hat. So if the null hypothesis is true, then this difference we see in the numerator is almost equal to 0 for all pairs of ij. And so if the null hypothesis is true, then the test statistic is very close to 0, as all differences we are squaring and adding here, all of them are to be close to 0 if HO is true. So they all are to be close to 0, and then this means that the test statistic as a whole is also to be close to 0. The second expression for the test statistic is a little bit simplified one. So it is, you see two formulas. You now see two formulas for the test statistic. So the first one is such that it's more easy to understand what's going on here, as we see this difference clearly, difference between the first sample proportion and the product of the two other sample proportions. And the second expression, it is just the same but a little bit simplified expression, more easy to calculate. It is more difficult to understand what's going on, as we don't see this difference clearly, but it's easier to calculate. So, and Charles Pearson, the mathematician who, actually he was not a mathematician, he was a psychologist, and he invented several statistical methods to apply them to his psychological studies. And so Charles Pearson proved that this statistic, the test statistic, follows chi-square distribution when the null hypothesis is true. So chi-square distribution with number of degrees of freedom equal to k-1 times m-1. So as you remember, in all hypothesis testing problems, we need to have a proposition, a theorem of this kind. So if the null hypothesis is true, then the test statistic follows some distribution. So here the distribution is a chi-square distribution. And as we understand that the test statistic and take only positive values, as you see that in the numerator we see square and in denominator we see only natural numbers. These n's all are natural numbers, so they are positive. So the test statistic itself is always positive, and we see that values close to 0 are in favor of the null hypothesis, and values that are far from 0, big positive values, are in favor of the alternative hypothesis. So this means that the critical region is right-tailed in this test. So we have one right-tailed critical region, and the border between acceptance and critical regions is the quantile of the chi-square distribution. And the p-value also can be found using the CDF of the chi-square distribution. So chi-squared CDF is difficult in so it is difficult to calculate values of the chi-squared CDF manually. So they usually do not calculate the p-values when you are solving a problem just manually, but when you are using some programming systems for mathematicians, they usually have the chi-squared CDF, so as a function that you can use. And so if you are testing this hypothesis, like or using Python or using R or some other languages, so then you have this function there. So this was the answer to the question whether it's better to think that our two variables are associated or not. So this was about hypothesis. So how we can understand which one the hypothesis on dependence or on independence seems to be more likely. More just probable. And sometimes we are also interested, not sometimes, always we are also interested in how strong the dependence is. So for example, the null hypothesis here is rejected. So we see that there is an association between A and B. So A and B are dependent. So, but how strong the dependence is? We want to measure it somehow. And there are several normalized coefficients, normalized association coefficients. You can see the formulas, namely they are Pearson coefficient, Chuprov coefficient, and Kramer coefficient. They're all based on the statistic of the Pearson's test. So capital H here in these formulas is the same as capital H here, is the Pearson's statistic. So, and all these coefficients can take values between 0 and 1. And so 0 means no association, 0 means independence, and 1 means such a situation that you can, that if you know A, you can just predict B without any error, without any mistake. So, for example, if the situation is such that you can, for example, if you know you have two nominal variables, like let's use consider the same example, gender and color hair, and hair color. And so, for example, if you know someone's hair color, you know the gender of this person. For example, all blondes are women and all red-headed people are men, something like this. If it is so, then these coefficients are to be equal to 1. So 1 means the association so strong that you can just predict B when you know A and vice versa. You can predict A when you know B. And so all values between 0 and 1 just show us how strong the dependence is. So one may ask, why do you show us 3 coefficients? So maybe we should choose one of them somehow. So which one is the best one? Which one is more convenient? Unfortunately, there is no answer to this question. That is why I show you three coefficients, so that they are all normalized, but they are normalized in a different manner. So, and it's up to you which one to use. So, they slightly differ from each other. So if, for example, you can see that for the same contingency table, the Chuprov coefficient is like 0.6 and Cramer coefficient is like 0.72. So they are not so very far, so very different, but they can differ, and so it's up to you which one you will use.